Okay, welcome back to 10.2 and no, not 10.3, just 10.2 for now. We'll do 10.3 later. 10.2 samples and populations. Now, the reason why I'm not combining, but the reason why I'm combining this into one slide, I guess you could say, is the 10.2 and 10.3 pretty much the exact same thing. It's just categorizing what's a sample, what's a population, what's a frequency, what's a parameter, what's a statistic, right? So that's what we're going to be talking about today. And it's going to be a really, really quick lesson. I think it's going to be like probably less than like 8 minutes. So let's start. We are going to examine the probability. Well, no. We are going to talk about what a statistic is and what a sample is and what a population is. Basically, that's just what we're going to be talking about. It's a lot simpler than 10.1. So what's the probability that you will roll 3 dice with the same number of dice on each one? What is it? Well, first of all, we're gonna do some counting. So the probability of rolling 3 dice, how many cases are there with the same number? We have 1, 1, 1. We have 2, 2, 2. We have 3, 3, 3. We have 4, 4, 4. We have 5, 5, 5. And we have 6, 6, 6. So those are the 6 cases. Those are the 6 cases where it's the same number on each one, right? And how many cases are there in total? Well, the first one has 6 choices. The second one has 6 choices, and the third one has 6 choices. So that's 216, 6 to the third. So then the probability is 6 over 216, which is which is 1 in 36, right? So 1 over 36. 36 to 1 is the probability of you rolling 3 dice. But whenever you actually test it out, right? This is the amount. I ran some simulations right here, and then I tried rolling 3 dice 36 times, which is I'm expected to get 1 roll from the 36 times with 3 of the same number, but I got 0. So the accuracy of this is it's not that accurate, right? But that's because we were rolling 36 times. If we were rolling way more than 36 times, we might have gotten 1, 2, maybe even like all 36, or maybe even all 36 of those dices are going to be maybe all 36 of those dices are going to have the same number on them. So I tried rolling the dice 100 times. Then now when I rolled those dices 100 times, I wish I could show you, but it would take way too long for me to analyze writing all the dice, rolling 1,000 times. Roll the dice 100 times, it'll be 2.78. That's the expected, and the reality is 2, so it's closer. 2 is closer to 2.78 than 0 is closer than to 1. Even on an arithmetic scale, that's closer, right? So 2 is a pretty good number of estimating the amount of the probability of the three dice being the same. The probability in this case would be about 1 in 50, which is better than 0 compared to 1 in 36. This is 1 in 50 compared to 1 in 36, right? So it's a lot better. Anyways, we are going to be talking about population and sample. So population means everything in the system, and sample means part of the system. Yeah. So part of the population, basically. So if you are to survey the population of the United States, were to survey population of Europe, Europe isn't a country. If you were to survey, I don't know, the population of North Korea, if you were to get a petition, then you will only be taking a sample. It will be a biased sample. Actually, it'll be pretty biased. With the people who want to accept the policy in the survey, in the petition, sign up for that petition. But the thing about the petition is, it also only access. There's also only a part of the population who access it. Same for most votes, most national votes. Only part of the population, maybe 40-60% of the population, actually vote because you can't get everyone to vote, right? We could the U.S. Census, even though the U.S. Census doesn't actually take care of everyone because it doesn't actually count everyone, even though there might be penalty for not counting everyone in your house. The U.S. Census doesn't actually count everyone. They might actually miss about 0.1% of the people. It still counts as part of the population because it's good enough, right? So the population of your classroom, if one person is absent, um, you kind of still just move on, right? If 15 people are absent, though, for example, if you're a teacher and you wanna give your students a test, right? If 15 people are absent, you probably won't give anyone the test. You probably wait until tomorrow till everyone's here. But if only one person's absent, he can make an appointment with the teacher to take a test on a different date. So population is taking data from everything in the system. There are some exceptions. And there are definitely real world exceptions, real world scenarios where they call something a population even though it's really not scientifically, mathematically. So coronavirus deaths, that's also the population of the world's coronavirus deaths, right? That's a population as well. So what's a hypothesis? The hypothesis is something that you learn in science. Actually, wait, let me go back. The data from a population is called a parameter. The data from a population is called a parameter, and the data from the sample is called a statistic, right? So if you if you roll the three dices, if you roll them 40 times, if you roll them 40 times and you roll them 36 times every time, so basically it's like 36 sets of 40 times. Each of those sets is a statistic, but the whole thing is a parameter. It's a little bit weird, terminology. But the whole thing's a parameter, and each of those sets is a statistic. So now we're gonna go to hypothesis. Hypothesis is a claim. It's like in science, you claim about a characteristic of a population, and if it's true or false, you want to know if it's true or false. You have to test it. So if you hypothesize a coin, that a coin is fair, not unfair, is fair, and you roll 300 times, would it be fair if the result is this, this, and this? This, you're gonna have to use your judgment, right? This, for me, is probably fair. 148 heads, 152 tails. There's some natural error, and you won't be able to. It's just random chance that you won't be able to flip a coin and get your desired result every single time, unless you have amazing reflexes, amazing muscle memory, and extreme luck, right? So 148 heads, 152 tails is probably fair. 212 heads and 88 tails. That's probably not fair because the amount of heads is more than double the amount of tails. So it's probably not fair. About 2.5 times. Um, maybe maybe the center of gravity is moved somewhere. Maybe it's dented on one side, so then it falls easier on the heads. No, it falls easier on the tail side, so then the head shows. I don't know, but it's not fair. What about this? Is this fair? Well, you really do have to use your own judgment because for me it's fair because it rolls heads and tails same amount of time. Now you have to be really lucky, really lucky to get two on the side, right? The chances, okay, for you guys who know how to use the choose notation, the chances of getting two on the side is astronomically low. Chances of getting two on the side is 150 choose two 150 choose 2 over I think I don't I think I got this right. I don't know, 150 choose 2 over 6,000 squared. That's the chance, right? So the chance is 1 in 6,000 or actually no, bigger, 300 choose 2. 3 300 choose 2 over 6,000 squared. The chances of getting one rule is 1 in 20. The chance of getting one roll is 1 in 6,000, so 300 rolls is about 1 in 20. But in order for you to get two of those rolls, you have to pick 2 out of 300 divided by 6,000 squared. Because that's 2 rolls, right? So 149 heads over. I don't actually think this is correct, though. That's the thing. So I think this is fair because it rolls the same amount of heads and tails, but maybe those on the side, maybe this coin very favors on the side more than heads or tails. Because most coins don't favor the on the side. There's a chance of 1 in 6,000, so it's pretty rare to get an on the side one. But obviously, it's your good judgment. 25. You perform 2 simulations of repeated selecting a marble out of the replacement that gets 3 red marbles. Yeah, I lied. This wasn't going to last 8 minutes. The first simulation uses 20 random samples of size 10. Second one, 400 random samples of size 10. Right? So the sample of size 10 means that the set, there's 20 sets of 20 sets, so every single time you every single simulation it's one set, and then they pick out 10 marbles, and the result for the 10 marbles it's is right here, right? It shows right here. 20 random samples of size 10 means 20 sets of size 10. That's basically what it means. So the histogram show, and then the second sample uses 400 sets of size 10. So the histogram shows the result. Which of those can you use to accurately analyze a hypothesis? And the one that you should use is obviously the second one, because this is actually, if you watch the previous video, this is a normal distribution, right? This doesn't look too great of a normal distribution. This looks like a better normal distribution. Right? This looks like a better normal distribution than this. This looks a little bit slanted to the left. This looks like a better normal distribution, so you should use this. But just in general, the more trials that you do with an experiment, the better it is. Right? That's something that you learn in science. So the more trials that you do, the more trials that you do, the better it is. This is relative frequency. So if you want to really analyze it, you can like break it into like mean and sigma, and mu, but you don't really have to, right? If you just draw these lines, kind of, you can already know how good it's going to be. For example, if you draw a line right here, and then you draw a line right here, and you expect it to be like this, but it's like this, it's probably not that good. You expect this to be like this, but it's like this, probably not that good. But these are a little bit better, as you can see. So, final question. This is just identification. We're just going to identify, and identify. That's why I put so many questions here. So, is it a population or a sample? Number of high school students in the United States. Population. Color of every third car that passes your house. Sample. Right, try to answer before me. Survey of 100 spectators at a sporting event with 1,800 spectators. Sample. Age of each dentist in the United States. Population. Okay, in 9 through 12, identify population and sample, describe the sample. Population, 1,152 adults, age 18. Actually, no. Population, not 1,000. Population, United States. Sample, 1,152 adults, age 18. And in the sample, 403 of them pretend to use their smartphones to avoid talking to someone. Right? Population, United States. Sample, 1,777 adults of age 18, and over 1,279 of them do some kind of spring cleaning every year. Population, school district. Sample, 1,300 high school students. And describe the sample, 1,001 of them like the new healthy cafeteria's food choices. Population, United States. Sample, 2,000 households. Describe the sample, that 1,280 of them eat dinner together every night. That's it. You see the pattern, right? Population, sample, and then the sample. Determine whether it's a parameter or statistic. Average annual salary of some physical therapist in a state is $76,210. statistic. That's a stat. Right? You've been using statistics all wrong. Right? If you say everything's a statistic, it's not. Some of them are parameters. But honestly, I think I'll keep saying everything is a statistic. I don't like statistics. I'm not a statistic teacher. So I'll just keep saying everything's a statistic. And I think because most people do, and I don't think that I'll not be doing it at any time soon. I won't be calling it a parameter because that might be confused with some computer science term or some math term. So, 53% of the senators in the United States Senate were Democrats. That is a parameter. 73% of all students in school would prefer to have school dances on Saturday. Parameter. Survey of U.S. adults found that 10% believe in this cleaning product they use is not safe for the environment. Now, this is a survey, and it's in specific, so I say it's a statistic. I say it's a statistic because it's a survey of U.S. adults, and they can't really, it's not really plausible. It's kind of superfluous. It's not really plausible to survey every single adult in the United States. So error analysis. 1,970 high school students found at 965 felt added stress because of their workload. So population is all the students in high school, correct? Sample is 965 students, wrong. It's not 965 students. But the 965 students who felt added stress, that's part of the sample. That's part of the sample, but the whole sample is 1,270 high school students, right? Okay, next. Of all the players on the National Football League team, mean age 26. Describe and correct the error and whether it's a parameter or statistic. Because the mean age of 26 is based on only one football team, is a statistic. It literally says of all the players in the National Football League team. Right? Even though it's based on one football team, that's the thing that we're looking for. We're looking for all the players in just one football team. We're not looking for part of the players in one football team. We're looking for everything in that football team. So even though it's one football team, we didn't specify that it's some football teams. It's just one football team. So therefore, it is a parameter, not a statistic. That is wrong. And that's it for this lesson. I'll see you next time for further categorization of samples and population.